Hello everyone, I hope you are doing well. So in this video, we are going to discuss Geeks for Geeks problem of the day, and today's problem is predecessor and successor, and it is a medium level problem. So if by the end of this video you feel that this video was helpful for you, then do consider dropping a like and don't forget to share your thoughts in the comments. Any general thing you would like to share or anything about the problem you felt, because your engagement with this particular video really helps the YouTube algorithm to understand that this video is actually helpful for you, and it will be able to reach more number of people like you who want to keep solving new problems. So this problem is like pretty similar to yesterday's problem, and this basically says that we have been given some key, right, and we have been given a binary search tree. Now we have to find the in order successor and predecessor of the given key. So basically, successor is going to be the smallest element which is greater than the key, and predecessor is going to be the greatest element which is smaller than the key, which they have also explained it here. The number just smaller, just smaller means that the greatest element smaller than the key, and just greater means that the smallest element greater than the key, right? So these are the things that we have to find, and if if any of them does not exist, we have to set it as null, right? So again, like the number of nodes 10 is power 4, and the expected complexity is height of binary search tree, and space is also height of binary search tree. Now, a very basic idea, let me just give you. Obviously, since the number of nodes are up to 10 is power 4 only, you can always traverse the whole binary tree in O of n, right? So it's a binary search tree. Now, when you will be traversing the values, how are you going to actually set the answer, right? So remember, like when I was explaining the problem, I used a specific term, that is the greatest key smaller than input, let's say, right? So this would be the in order predecessor, and in order successor would be smallest key, it should be T, smallest key greater than input, right? So there is a reason why I said it like this, because this is the important thing that you have to understand. They have said that the key just greater or the key just smaller, but this is what is actually going to mean when you write the code, right? How do you identify which is the just next key to a key, right? Or which is the just greater key to a key, or what is the just smaller key to a given key, right? So this is the definition that you will be using to identify those keys, right? Now what you can do is you can just traverse through all the nodes, right? So I'm just telling a simple approach first. So you can just traverse through all the nodes, and for each node you can check whether the current key, let's say the current node's key, is less than your original key, right? So you will have to update your answer in the predecessor, right? And how will you update it? You will update it only if the new key that I'm encountering is actually greater than, right? So we have to find the greatest key, right? So we will update only if it is greater than the key already present in the predecessor. Either predecessor would be null, right? In that case, you directly replace the predecessor with the current node. Otherwise, what you will do is you will update the key only if the current node's key is greater than the key of the predecessor, right? Similarly, you will also check one condition: if current key is greater than the original key that has been given to us in the input. In this case, we will have to update the successor, right? And we'll always update the successor only if either the successor is already null, right? It is not pointing to any node, or the key that it holds is actually greater than the key of the current node, right? So we will have to replace it with a smaller key. This is our whole idea. Now, if at each node you do these two steps, and after it you just call DFS on current of left, so not actually DFS, you can call it DFS, or it can be like a traversal function also. So you can call it on current on left, or you can call it on current on right. Right? You can simply call this DFS function into both of them. This approach would definitely work. It's just that its complexity would be O of n, since you are visiting all the nodes, right? Now, what you have to do is you have to optimize it somehow so that you visit like only login nodes at maximum. So the exact time complexity is going to be 2 log n for this particular problem. Let me discuss why. So if I am at this particular node, right, there might be a case that the successor and the predecessor lie on two opposite halves. right? So I have to go in both of those halves in this particular case. I have no choice rather than to go in both of the halves. The only thing that is optimizing my cost is, like for example, this is my key, let's say 10, and my original value of key was let's say 20, right? So this is 10, this was 15, this was 18, right? So you see, all of these keys are less than 20. No matter where I go, I will always be able to find the predecessor. I'll not find the successor, but the predecessor. So is it very optimal to go to the left half? No, it is not, because here I will find 10 and here I will find 15. I always want the greatest, so I will always go move towards the greatest. But let's say the key was 15, right? And in this case, one side I'll find the predecessor, one side I'll find the successor, right? So I will have to go to both of the sides. So you will at least have to traverse 2 times the height of the tree. Now, like in this particular case, for example, the tree was like this and you decided to go further. So in the left half, you will be going to the right side, because this is the way you will find the greatest element. In the right half, you will be going to the left side only. This is the way you will find the smallest element, right? So one way of doing it would have been, like, you find the input key that you are looking for, and you go to its left half and just traversing through the right side always. And we go to the right half and we just go to the left side always, right? This is similar to the approach we use in deleting some node from the binary search tree when we have to find the in order successor or in order predecessor, right? If you remember it correctly, this is the way we do it. But the problem with this approach is the key may not always be present in our input, right? This is the problem. So we cannot check on the basis of the current key. We will have to check on the basis of its children, right? So if the left child is smaller than my current key, that means I can find my predecessor there. If my right child is greater than my current key, that means I can find my successor there, right? If both of them are smaller, I would always move to the right side. Why? Because I want to find the greatest predecessor, right? Or the greatest value that is smaller than my key. If both of them are greater than my key, then I'll have to find the smallest key. So I'll move to the left. So this way I'll be eliminating some of my steps and reducing my complexity from overall O of n, right? So it will be some log n multiplied by some constant factor, right? It is not necessarily 2, because in some cases you will always have to visit more number of nodes. So but it is much better than on n, because now in this case you will be definitely omitting some of the key states. So this would be the approach that will be going on, and let me just explain this to you very briefly again. So what you essentially have to do is, since we have discovered that we don't need to traverse all the nodes, we will check what are the keys representing, right? If the left key is smaller than my input, that means I have a possibility of finding my predecessor there, right? So I'll move on to the left to find the smaller node. If my right key is greater than my current node, right, that means I have a possibility of finding my successor there. So I'll move on to it. But if both of them are smaller than the key input key, that means both of them will have a predecessor, right? So it is definitely more optimal to move on to the right subtree, because I will find greater values there. If both of them are greater than the key k, that means in both of the cases I'll find my successor. So it is always optimal to move to the left side. Why? Because I want to find the smallest key greater than the input, right? So this is how you can decide which side you have to move, and accordingly you will find your answer. So let me just show you the code I have done. So you'll have to just implement a couple of checks. Other than it is very easy. So I've created 2 nodes, or rather I've not created them. I just set their value as null pointer. They're being passed as to me as input, right? Now I just call my DFS function from the root, and I check whether current key is smaller than the key, right? Current node's key is smaller than the input key. Then I check either the predecessor should be null, right, or predecessor's key that it is currently holding should be less than the current node's key. In these 2 cases, I'll update my predecessor, right? Otherwise, I check if current key is greater than the input key. In that particular case, either successor should be null, right, it should not have any key, or if it has a key, that should be greater than the current node's key. Only then I'll update my successor. Now, in all other cases, now I have to create some logic to traverse the tree, right? So if both of them are null pointers, right, if both of them are null pointers in my current, then what I'll do is I'll just check whether both of them are smaller than my key or not. If both of them are smaller, that means both of them will have some key smaller than my current key. So I have to take the greatest of them. That is why I am traversing to the right. If both of them are greater, that means I have to take smaller among the two. So that is why I am traversing to the left. In the other cases, if one of them is smaller, one of them is greater, I have to traverse both of the sides to find my correct answer. Right. One of them or both of them are null pointer. I'll check if any one of them is not null pointer. I'll visit that particular node. If left is not null pointer, I go to the left. If right is not null pointer, I go to the right. Right. So at the end, I will have my answer in predecessor and successor, these two variables. And since it is a void function, I don't have to return anything. It will automatically take their value since they are passed by reference. So this would be the solution of today's problem of the day. Now let me just quickly submit it and show it to you. So you will see that it passes all the test cases. Yeah. And there is one more thing that I wanted to show you. Let me just quickly show it to you from my submissions. So I also tried the other approach where you don't have to apply this complex logic. You can just check whether it is not null pointer and you can just directly visit the left and the right half respectively. It will still work due to the number of nodes, but it is not the expected time complexity. That is why I still wanted to show you this particular approach. So I hope that you guys were able to understand the solution. If you guys did, consider dropping a like on this video and don't forget to subscribe to this channel. It's always free of cost and you can always unsubscribe later if you don't find the videos interesting. So share the channel with your friends. Until the next video drops, keep coding, stay safe, bye.